All right, guys. Well, this is going to take place of our class on Friday instead of the advising day. So we left off, or sorry, because I'm having the advising day, we're not having in-class session for XViz. So this is where we left off. We're in the aerobic adaptations to, the chronic adaptations to aerobic exercise training. And we just talked about this, which is what drives ventilation. Talked about how CO2 is the main driver of ventilation. Okay, and then we come to this slide. This is a classic study that looked at an untrained person versus an elite trained runner. Okay, and so on the x-axis is their work rate. What percentage of VO2 max are they at? On the y-axis is either their ventilation in liters per minute or the pH of their blood. Okay, and so normally I would have you talk about this with the people around you, figure out what's going on, write some observations and some conclusions, but we're not doing that since we're not in class. So let me talk you through it. So the couple important things to note are, number one, this pH starts dropping at about 50% of max in the untrained person. In the trained person, we don't see a super significant drop till here, and then even more so here. This is closer to 75-80% of max. Okay, at that same point, we see the increase in ventilation, or that ventilation threshold that we've talked about before. Okay, so the first question will be, how are pH and ventilation related? Right, and so we see that we know that pH is related to ventilation because hydrogen ions get buffered, right? And then they, through the bicarbonate buffering equation, they eventually, that forms CO2 when they get buffered, right? And we just said CO2 is the main driver of ventilation. So what does this tell us if ventilation threshold moves out, right? This is ventilation threshold, that point where the ventilation is going up, and then all of a sudden it starts going up steeper. Right, change in that relationship, nice and straight, and then boom, steeper up. Right, so it went from about, the ventilation threshold went from about 50. So VT, ventilation threshold, went from 50% up to probably about 80% of max with training. Okay, maybe 75. So the question is, what causes that? Right, what causes that ventilation threshold to occur so much later? And we know how that's connected to lactate threshold, right? Because the lactate threshold and the anaerobic glycolysis is what's producing this, right? So lactate is going to lead to that hydrogen ion release, okay? We know that comes from the glycolytic system. That's what produces the lactate. Okay, so the question is, why do we have less lactate produced earlier in, as far as percentage of VO2 max goes, in a trained person? Okay, and so that's really what we need to think about, is what changes to move this ventilation threshold out so we can keep a more normal pH for much longer when we're trained versus only early on here. And this is going to have a lot to do with fatigue, right? The faster this pH drops, the faster we start breathing hard, and the faster we get burning in our muscles. Okay, so the big thing that's really going on here is, first of all, we are able to use, for any given sub-maximal intensity down here, the person who's trained uses less of their glycolytic system. Okay, if you use less glycolytic system, they produce less lactate, and they will produce less hydrogen ion, less hydrogen ion. Okay, that's going to lead to less CO2 production, which is going to lead to a decrease in ventilation. Okay, and the reason they can use less of their glycolytic system is because they have a more powerful oxidative system. All right, if you have more powerful oxidative system, the body always wants to use the oxidative system instead of the glycolytic system if it can, but it just uses the glycolytic system if it has to. Okay, so once we train, we become more powerful with our oxidative system, so we can we don't have to kick in so much of our glycolytic system so fast. Okay? We've also gotten better at dealing with the lactate that does come out, so that helps too. We've gotten better at circulating blood to the muscles. Okay, we're going to talk about all those things, but the key here is that we reach lactate threshold and ventilation threshold later in as far as percentage of VO2 max goes, because we have a more powerful oxidative system, which leads to less use of the glycolytic system, which leads to less lactate production, less hydrogen ion production, less CO2 production, and a decreased ventilation. Okay, so let's talk about this a little bit more via this clicker question. So this question is, your friend notices that they're breathing a lot less intensely while running at 8 miles per hour after training for 2 months before they started training. Okay, so they ran on the treadmill at 8 miles per hour the first time before they started training. They kind of remembered how hard they were breathing doing that. They trained for 2 months, did aerobic training for 2 months, did a lot of running, stuff like that, for 2 months, come back on the treadmill again, and they noticed, wow, I'm breathing, and still at 8 miles per hour, they noticed they're breathing a lot lighter, not breathing as hard. Okay, so why is that? Okay, definitely they're producing less CO2, right, with the mechanisms we just talked about. They're using their glycolytic system, yes, for sure. They're using their glycolytic system more, nope. They're using their oxidative system more, yes, for sure. Using their oxidative system less, no. Okay, so A, B, and D are correct there. Okay, so one thing I want us to think about with all of the changes that we talk about are going to be, how does each factor change at rest? How does it change submaximally and maximally? Okay, so the definition of submaximal is going to be just anything between rest and max. Okay, so the way that I'll typically phrase a question would be just like I did on this clicker question. If they were at 8 miles per hour before training and again after training, and we know that 8 miles per hour was below their VO2 max both times, then we would consider that a submaximal bout of exercise. Okay, so at rest, what do you think ventilation does? Ventilation does not change at rest. So I'm going to put a sideways arrow like this, no change in ventilation, resting ventilation. Submaximally, that 8 miles per hour before and after, definitely ventilation is going to go down because we don't have as much CO2 driving that ventilation up. Lastly, maximal exercise. Well, in order to increase VO2 max, we have to increase ventilation. So definitely that's going to go up. We can see changes like this, maybe maximal ventilation from 100 to 120, up to 130 to 150, going from untrained to trained. I've seen ventilations up over 200 liters per minute in some of our students here at Point Loma, so they can get quite high. And that change in ventilation, what's it caused by? Is it caused by changes in the lungs themselves? The lungs get stronger? Not really, okay? All we're really doing is tapping into the power of the lungs that we already had. So all we're doing is we're just pushing those lungs further into the capacity that was already there. We're not really training up our lungs to be stronger. We're actually just driving them further with higher levels of CO2, higher levels of metabolism, because other parts of the body can handle that. So really just tapping into the power that was already there in the lungs. Okay, so that's the ventilation piece. Done with that. Let's move over to central blood flow now, or the heart. How does the heart change with exercise? Okay, let's talk about heart rate first. Okay, this shows sedentary at rest, sedentary at max. This shows a trained person at rest, a trained person at max. Okay, so what do we see? Maximal heart rate, 185 to 185. So, no change. We don't ever expect a change in maximal heart rate with training. Sometimes it might go down a little bit, but it's usually almost never going to go up. Okay, what about resting heart rate? Well, that went from 75 to 60. That goes down. Okay, we're going to talk about why in a second, but this has a lot to do with stroke volume, right? If stroke volume goes up, then heart rate can go down, and we can get an equal cardiac output. Okay. All right, so that was looking at rest and max. What about submaximal, right? Submaximal will be anything between resting down here and maximal up here. And what we see pre-training in the green line, post-training here in this purple line, we see each point is a little bit lower, right? Even more pronounced the higher up we go. Okay, right there, maximal, oops, excuse me, sorry about that, thing. Maximal ends up being similar, maybe down by 1 or 2 beats, but not much, right? So that maximal heart rate doesn't change much, but we do have a decrease in submax heart rate. And this is by treadmill speed, right? So at 15 kilometers before training, they were at about 175. 15 kilometers after training, they're at about 155. So it went down by 20 beats or so, 18 beats per minute. That's a lot. Okay, so why does it do that? Again, stroke volume goes up. So if stroke volume goes up, then heart rate can go down, and we can keep the same cardiac output, because heart rate times stroke volume equals cardiac output. If stroke volume goes up, this one can go down, and we can keep cardiac output the same. Okay, so so next let's look at stroke volume. All right, we just kind of already talked about with the other two, but this would be those same things. We got someone who's sedentary at rest and max, someone who's trained at rest and max. Here's stroke volume at rest, stroke volume sedentary rest, stroke volume trained rest. We see a 20 mil increase in resting stroke volume. Okay, so that one definitely goes up. What about maximal? Going from 120 to 60, sedentary to trained. That one definitely goes up too. Okay, so this would explain why resting heart rate is lower, and why, but this doesn't necessarily explain why maximal heart rate is not lower. Okay, we'll get there in a second, but I can give you a little hint for now. The key here is that we actually want to have a greater cardiac output, right? At rest, cardiac output is the same pre and post training, right? We don't need to have a greater resting cardiac output, but at maximal exercise, if VO2 max equals up, then we know cardiac output is also up. And so that's a key feature. So it's up because heart rate was the same, but the other variable went up, right? Stroke volume went up. That would lead to a greater cardiac output. Okay, that was rest and max again. What about submax? Okay, submax stroke volume. Okay, each step of the way we have a little bit of an increase. Not huge in the beginning, gets bigger as we go out, right? Each step greater. This person obviously just can go to a higher treadmill speed than they could before, so that would definitely mean their VO2 max was higher. Okay, so pretty large change in submaximal stroke volume, all of that. Okay, so increase in submaximal stroke volume. This going from their maximal stroke volume before of about 110 maybe up to about 150 something is a huge change in maximal stroke volume. So submax goes up and max goes up. Again, this increase in submax is what allows for submax heart rate to go down. Okay, so then what about cardiac output? Because all of these variables are really just getting us closer to cardiac output, right? So again, we got them all here. Okay, well, we have at least a 5 kilometer per hour treadmill speed first. We work our way up, pre-training, post-training. We don't see much in here. Those dots are pretty close to each other, but then we start seeing a difference here. Maximal cardiac output went from maybe 21 liters per minute up to maybe 26, 27 liters per minute. Okay, so that's max cardiac output. All right, so submax cardiac output, no change. those dots are very close to each other, not much of a change. Okay, but maximal definitely goes up. And resting cardiac output is also no change. That's just driven by the requirement. We don't require any more oxygen at rest after we're trained versus untrained. Okay. So let's talk a little bit about how that actually changes. What's the physiology behind changing stroke volume? We know the physiology behind changing heart rate is that the nervous system controls that, but the reason it can do that is because stroke volume is higher. Okay, so what is the physiology leading to those changes in stroke volume? Okay, this diagram is very nice from your book. It looks at 3 different factors in the heart in elite runners, cyclists, and strength athletes. This looks at a difference from control. Okay, so they compared these elite athletes to just regular sedentary type people. Okay, this one here is left ventricular internal diameter. Okay, so this one's internal diameter of left ventricle. This one here is called the median wall thickness. Okay, and this one here is left ventricular mass. This one's just like the weight of the left side of the heart, right? Really the mass, but just how big the heart is. This one is a good look at how thick those walls are, how thick your heart muscle is. Okay, so the interesting part here is that we see a 10% greater internal diameter of the heart in both the runners and the cyclists. Nothing much to speak of in the strength athletes. Okay, median wall thickness, we see 15 to 20, even up to 30% greater thickness in all 3 of them. Okay, so definitely higher here in the runners and the strength athletes, but then the cyclists are even higher than that. The big reason for that, and this is showing that the heart hypertrophies, right? Same thing with left ventricular mass. The heart of those runners is 50% larger than the heart of the sedentary people. Heart of the strength athletes is maybe 25% larger. Heart of the runners is over 60, around 65% larger. The cyclists, sorry. So obviously we see major increases in both the diameter, the open space in the heart with training, and then we also see increases in the actual thickness of the muscle, so we get hypertrophy of those cardiac muscle cells. Okay, the one thing you might be wondering is why the strength athletes look so much different, really maybe even why the cyclists look different. Okay, the difference down here with the left ventricular internal diameter is explained by the fact that the stimulus for increasing the strength of the heart with weightlifting or strength athletes, all the stimulus is just high blood pressure that the heart has to push against. It's not that weightlifting requires a great cardiac output, so we don't actually need to get more blood out in response to that, not very much at least, but we need to push blood out against a lot higher blood pressure, a lot higher afterload, right? So the internal diameter doesn't really get much bigger, but the heart gets thicker and stronger, shown by the next 2. So we can't, so the heart gets stronger to push out blood over that greater afterload, but the internal diameter doesn't actually get that much larger. Okay, so that's why the difference in strength athletes, but then the cyclists obviously have much bigger hearts than the 2. Okay, and the reason for that is purely just because cyclists are bigger people. Okay, it's much more advantageous for a runner to be a small person because they're carrying their whole body weight, whereas cyclists are typically bigger people. Your average marathoner might be 110, 125 pounds. Average cyclists are going to be more like 160, 170. Bigger people means bigger hearts, so that's really what explains that. Okay, so the key factors to kind of explain what we were just talking about on that graph is that left ventricular chamber size and wall thickness increase. And this actually happens to start after 1 week of... All right, so again, the factors within the heart that help us increase stroke volume are, first of all, we have an increase in wall thickness. Okay, that's what we just saw. So that's like thickness of the walls of the left ventricle. This can be somewhere around 12 to 14 millimeter increase. Okay, but then we also have a proportional increase in left ventricular diameter. That means the internal chamber, right? That really helps us fit more blood, right? And this is in response to endurance training. Okay, and then we also see increased left ventricular contractility. Okay, this is due to an increased calcium sensitivity. As well as increased diastolic filling. Okay, and that's due to a couple things. That's due to the fact that we have, at least submaximally, we have a decreased heart rate, so that leaves more time to fill. Right? And that's going to, the heart rate's going to allow for increased blood volume, increased venous return, and so then the result of that is a improved length-tension relationship. So that's the whole Frank-Starling mechanism. If we get more blood in there, we're increasing preload, and that's a huge factor. Increasing preload is going to stretch out the heart more, improve length-tension relationship, more bounce back, all of that. Okay, so that's the heart itself. Okay, and that really could have gone down there as part of number 4, but it's really all kind of similar idea. Okay, so then what else changes besides the heart itself? Actually, the most important thing early on is an increased blood volume. And we get that via increased plasma and increased red blood cells. Okay, so we'll get to that in a second when we talk about the blood, but you can't really talk about an increase in stroke volume without talking about that because that's so huge. Okay, so the heart gets stronger, bigger, more powerful, and then we get more blood to pump in there as well. Okay, so let's look at some of those factors here on these graphs. We're going to come back to these on in the TBL days for sure, but if we look at these graphs, we can really figure out how stroke volume changes, right? So we have end diastolic volume here, and systolic volume there, and ejection fraction there. So we can actually calculate a couple things here, right? We can calculate end diastolic volume, we can calculate stroke volume, and end diastolic volume we have here. Okay, if we had heart rate, we could do cardiac output, but we can't quite get there. But we see an increase in resting end diastolic volume. Okay, from maybe about a 20 mil increase in resting end diastolic volume. Okay, so we're getting more venous return, right? So this represents an increase in preload. Okay, that's at rest. Okay, at rest we have the no change in ejection fraction though. Okay, so no change in contractility at rest. That's shown here. Pre-training, post-training, we actually have a little bit of an increase in resting and systolic volume. Doesn't really affect us too much. Okay, so then we go up from resting to exercise. We see an increase in end diastolic volume in both. Okay, it kind of flattens out, and then it goes up even more with training. So this increase in maximal end diastolic volume is pretty huge. It's close to 30, 25, 30 mLs, and that's going to be a huge increase in preload, which accounts for a lot of that increase in stroke volume. Okay, and systolic volume pretty much stays the same, right? It doesn't change too much. But the amazing part about that is that we started with way more blood, right? We had 30 mils more blood here at rest, and then we actually even end up with less blood in there, just a little bit, maybe down from about 45 to about 38 or something, right? So we actually end up with less blood in the heart, even though we started with so much more. So what does that result in? that results in a huge increase in the percentage of blood that came out in ejection fraction. Excuse me. Okay, so this ejection fraction represents the increase in contractility. And those are our two big things that change. Preload increases, shown by end diastolic volume. Contractility increases, shown by this change in ejection fraction, as well as shown by no change in ESV, even with our huge change in the diastolic volume. Okay, so it changes with training by increasing preload and increasing contractility. All right, we'll come back to that a little more in the TBL day as well. Okay, so just kind of a little review of what we just talked about with ventilation. In most cases, after training program, maximal ventilation, it's got to go up, right? Or else we couldn't increase VO2 max. Resting ventilation, not going to change much. And submaximal ventilation can go down, right? So increased, unchanged, decreased is D right there. That's what we want. Okay, which of the following factors are responsible for the increase in stroke volume due to training? We just talked about those, right? We got increased plasma volume, increased cardiac contractility, increased chamber size, increased end diastolic volume, increased red blood cell volume, and increased wall thickness. All of them. Good stuff. All right. Okay. So lastly, let's talk about peripheral blood flow. How do those capillaries and arterioles change for us? Okay, so training and the blood itself. So training can cause an increase in blood volume. Hypervolemia, okay, is one of the quickest changes that happens. 20 to 25% larger blood volume in endurance trained people versus normal, okay? And then just with the beginning of an endurance training program, the first week and a half, we see a 10% increase. Okay, the question is, where does that fluid come from? When we exercise, we increase blood pressure so much that we're pushing out our plasma volume, like we already talked about, right? We push out that plasma volume, and then the liver senses that as, oh shoot, we need to add more plasma. So it does that by making more plasma proteins. Okay, so it pushes out. We also don't just push out plasma; we push out plasma proteins. The liver responds to that by liver makes more plasma proteins. Okay, and the kidneys respond to that decrease in blood volume that got because the plasma got pushed out, and said, shoot, we need more water here. So then the brain is going to cause the release of the hypothalamus and pituitary is going to cause the release of ADH and aldosterone. So we increase water retention. Okay, so the two mechanisms for the extra fluid is the increase in plasma proteins and these hormones helping us hold on to more water. Okay, so this definitely helps with thermoregulation because we can sweat more. With no effect on preload, right? And we can send more blood to the skin to cool us, again, without affecting preload as much. And so with that, if we don't affect preload as much, if we have enough blood still to send back to the heart, even though we've sent all this blood to the skin to sweat and to cool us down, then stroke volume doesn't go down as much, and so we can maintain stroke volume. But even with all this extra blood, we definitely will increase stroke volume. Okay, and that's a key factor. Okay, so here's what it looks like. We go from, if this is what our blood looks like, we've got the plasma up here on top, red blood cells down here. We go from a hematocrit of 44 to begin with, goes to 42. Wait, that doesn't seem like a good change. But look at, we've got 2.2 liters of red blood cells and 2.4. So we did increase RBC number. We got that. But the plasma volume went from 2.8 to 3.3. So that increase in plasma was greater than the increase in red blood cells. So we overall decrease hematocrit. Goes down, but both plasma goes up and red blood cells went up. It's just the plasma went up more. Okay, so the plasma went up. We already talked about that. Why do red blood cells go up? Well, because when we're exercising intensely, the kidneys sense decreased oxygen levels. That stimulates the release of erythropoietin. That goes to the bone marrow, causes red blood cell production, and we increase red blood cell count. Okay, what about the blood vessels themselves? We talked about the blood. What about the blood vessels? What changes do we see in capillary density? We can look at this little figure from your book. We see capillaries per millimeter squared of muscle. Okay, and then muscle fibers per millimeter squared, and capillary to fiber ratio, and diffusion distance. Okay, first of all, capillaries per millimeter. We have well-trained on top, untrained down here on bottom. So we have more capillaries per area per millimeter squared after training. Okay, muscle fibers per millimeter squared. We have less of those. Okay, per millimeter squared of capillaries. So what that means is there's more capillaries. It's a higher capillary to fiber ratio. That's really what that's showing as well. More capillaries for every single muscle fiber we have. We have more capillaries to feed it. And probably the most important part is that the average distance from a capillary to a muscle fiber has gone down. And that's the most important part. So we can diffuse more oxygen out of the blood, get it to the muscle, so we can use the oxidative system better. Okay, so this is capillary density. Trained athletes have about 30% greater capillary density than sedentary. 2 months of endurance training can increase capillary number by 50%. Okay, type 1 fiber is definitely the highest density, and this affects diffusion because it decreases diffusion distance, so then increases amount of O2 diffused. Then, by increasing the amount of O2 diffused, we can use the oxidative system more. Right? And so then this would have to affect AVO2 difference, right? If we diffuse more oxygen, that means we have a lower oxygen value when it gets to the venous side. So it's a big part of what increases AVO2 difference. Okay, and here's some numbers to show that AVO2 difference. At rest, at rest, there's no difference in AVO2 difference, sedentary to trained. So no change here. Oops, sorry. No change there. But what about at max? We go from 14 to 16. So there's definitely an increase there, partially driven by the capillaries. We'll talk about some other reasons as well. Okay, so we will leave it off right here and pick this up next week.